So I'm now going to go through this question 11 on the C4 differentiation thing. So I didn't mean to do that. I wanted to do that. Yes, there we go. So the first bit of the question is, using the derivatives of sin x and cos x, prove that cot x will differentiate to minus cosec squared x. So it's literally telling you to use sine and cos. So we're going to start with y being cos x over sine x. And then we're going to use quotient rule to do that. So we'll start with f of x, not g of x. I don't know why I put that. So let's start with f of x. F of x will have to be the top value, so that'll be cos x. And then our derivative of that, it will become minus sine x. And then g of x will be the denominator, which is sine x. And then the derivative of g is going to be cos x. So let's put that now into quotient rule. So putting that into quotient rule, we are going to get that we do the g of x times by the derivative of f of x first. So that will become a minus sine squared x. And then for quotient rule, it's take away f of x times by the first derivative of g of x, which will be cos squared x. And then that's all over g of x squared, which is sine squared x. So that is what it would differentiate to. But we want to prove that it's 1 over cosec squared. Now, when you're rearranging this, because we're going to have to, we need to think about what we actually want here. I want cosec squared. Well, cosec squared is 1 over sine squared. I've already got that on the bottom here. So I think it's the top that I need to sort out. And what I'm thinking here is I can factorize out that negative. That looks like a sad face. It's not what I meant to do. So I'm going to factorize out and make that sine squared x plus cos squared x. And I'm hoping we know what that is equal to. So sine squared x over cos squared x is just 1, isn't it? So we can make that whole thing now minus 1 over sine squared x. And I know that 1 over sine squared is cosec squared. So that just becomes minus cosec x squared, which is what I wanted. So that's the first part of the question. So we're looking at part B. So part B is asking us to show that the curve with that equation has no turning point. So what are we thinking mathematically? What is that trying to get us to prove? It's trying to get us to prove that basically the dy by dx, it can't equal 0, because that's the only time we're going to get a turning point is when the rate of change is 0. That's what a turning point is. So firstly, I need to find what dy by dx is, and for that I'm going to use quotient rule and also looking at what I did in part A. So I'm just going to write out our function. So it's e to the x cot x. So f of x is e to the x. First derivative, I don't know what I was trying to write there, is still e to the x. And then g of x is cot x. And we know what cot x differentiates to because that was part A of the question. That differentiates to minus cosec squared x. So if it's part A, part B, always look at, is the thing you've just done helpful? That's just exam technique at this point. So then let's work out what dy by dx is going to be. So g of x times by f dash x, that's just e to the x cot x. And then that'll be plus f of x times by the first derivative of g of x. But I can see it's minus cosec there, so it's going to become plus instead. So it will be e to the x cosec squared x. So apologies for the noises. I've got builders in, so if you can hear anything, apologies for that. So I'm going to factorize out e to the x because now I'm at that point where I need to prove that this can't equal 0. So I think my first step to doing that is doing this. So cot x plus cosec squared x, like so. So to prove that dy by dx, well, to make it equal 0, either e to the x has to equal 0, or cot x plus cosec squared x has to equal 0. One of those things must be true. So e to the x can't equal 0. It can't happen. It doesn't work. And that is because if we, let's think if we tried to even do anything with that. So if we did, if we natural logged both sides, we get x is log of 0, and log of 0 is undefined. Log of 0, it doesn't happen. It's undefined. So therefore, if x is the log of 0 in that situation, and it doesn't happen, e to the x simply can't equal 0. So that's that first bit dealt with. Okay, so we've done the e to the x bit. We now need to deal with this cot x plus cosec squared x here. That's what we need to deal with now. But I've just realised that I have made an error here. That is a minus there. Because we're not doing quotient rule, we're doing product rule. So it would have been a plus, and because we got minus cosec up here, because that's minus cosec squared x, it will become a minus. So wherever I said before, it should be a minus. So just be careful of that. But anyway, so now we're dealing with, the cot x minus cosec squared x there. So let's, again, it's one of those things where at the minute we might not see it. So we just sort of need to play about with it a bit and see what's going to happen. I might change my colour just so we can tell what I'm working with. So I'm basically trying to prove or see if this can equal 0. Because remember, to get dy by dx equals 0, either e to the x has to equal 0 or the bit in the bracket equals 0. So we're doing the bit in the bracket now. So that means that cot x equals cosec squared x. I've put the squared into there, haven't I? So now what we can do here is, I don't know about you, cots and cosecs, I want to write them in terms of sine and cos. I think that's probably going to be the most helpful thing for us to do here, because then we can start seeing if there's anything that can cancel out, etc. So cot, I know, is cos x over sine x. And then cosec squared x is 1 over sine squared x. So what I could do here is, I think I could multiply both sides through by sine x. So I'm going to do that, and that will get rid of that sine x there and get rid of the squared there. So we end up with cos x is equal to 1 over sine x. I end up with this thing here. So I don't like that x. So then let's get all the coses and sines together, because I'm hoping you might recognize this form from somewhere. So if I rewrite that, so now we get cos x sine x is equal to 1. Now you might want to consult your formula booklet or something here to think about, where have we seen cos x sine x before? You can get that from the double angle formulae. So if we take our sine A plus sine A is equal to sine A cos A, so it would be sine A plus sine B, but we're using the same thing here. So sine A cos A plus cos A sine A. So that's just in the sort of the angle formula notation. So that gives me that sine 2A here is equal to 2 sine A cos A. So doing a bit of manipulation on that thing there, hopefully we can see that if we divided through by 2, we get sine 2A over 2 is equal to sine A cos A. So this is the tricky thing to spot here. So what we can do now is we can actually replace sine x, cos x sine x. We can replace that now with sine 2x over 2. So cos x sine x is equal to sine 2x over 2. So that is now equal to 1. So therefore, sine of 2x is equal to 2. And then this here, we need to think about what sine x or what sine 2x looks like. Well, sine x, if it's just, I know there's a 2 there, but that has a max value of 1, doesn't it? In, if we think about what our graph looks like for our sine graph, again, I know 2x, it'd be squished. So you'd have, 2 of them in 360. But its max value for y is minus 1 and 1. 2's not in the picture. So the maximum value of sine 2x is 1. So max value of sine of 2x is 1. So therefore, sine 2x can't equal 2. It just doesn't happen. So therefore, there's no solution there. So that means we have no solution. So we've concluded, so this is the main bit that I want to get at here. So because of this, because that's not got no solution, and because this thing here, again, is undefined at this point, so therefore there's no solution here. I can put, if you want there, we can put no solution. So because both of those have no solution, if we try and make them equal 0, therefore it can't have any turning points, because we cannot make the y by dx equal 0, and it's those two things that we need to state to do that.